Good afternoon, everybody. It's a great chance for us to show our recent work here via this conference. I'm Yunfei Teng from Dalian University of Technology. Here also lists some of my colleagues who also contributed to this work. Some of them come from Dalian University of Technology, and some come from the University of Western Australia. My supervisor, Professor Liang Cheng, is also included here. Okay, I would like to start. My topic is a defect function model for 1D wave boundary layer. 1D wave boundary layer is an ongoing topic till today due to its significance in coastal engineering applications. Here we focus on the defect function approach and will not do much comments on other approaches. The defect function chi is only the function of Z and represents the velocity difference between wave boundary layer and the free stream. The Stokes solution is the most basic form of defect function. And here the Stokes solution beta and the spatial temporal velocity deficit per se are introduced. This figure is a sketch for the velocity deficit governed by the Stokes solution. We would like to quantify the spatial and the temporal structure here based on this Stokes solution. Taking the phase omega t being 0 as an example, eta1 and eta2 represent the elevations where psi being 0, which indicates the instantaneous velocity in wave boundary layer is equal to the free stream. And another definition of wave boundary layer thickness denotes the elevation of the maximum velocity overshoot. Here's overshoot. Velocity overshoot means the velocity in the boundary layer is larger than the free stream. For Stokes solution, these three elevations are readily to solve, and they are called the spatial structure. We plot the spatial structure as a function of phase. It's found that the spatial structure increases or goes up linearly with time, and the development of spatial structure along time or phase is called temporal structure. The sudden drop happen at half pi is due to the reversal of flow direction. Differently, we will say the temporal development of the structure is non-linear, is not linear in a turbulent wave boundary layer. It develops slower in the accelerating phase and faster in the decelerating phase. This behavior is related to the development of the extent of wall turbulence. It's inhibited in the accelerating phase, whereas it's not in the decelerating phase. Here comes the question: how can we quantify the structure of a turbulent wave boundary layer with a defect function approach? Before we make further investigations, we would like to give a brief introduction on how to use defect function approach. Consider the temporal velocity deficit and a general form of defect function, which is written as a function of x1 and x2. Fit the measured velocity deficit with these two formulas, we can get the value of x1 and x2. Then we can plot x1 and x2 against z in a log scale like this. Starting from x1 and x2, all the existing forms of defect functions are trying to establish correlations between x1, x2, and z. Here we list a few typical forms. DFS, proposed by Sleeth 1982, assumes x1 equal to x2. It has two length scales. On the contrary, DFN, proposed by Nielsen 1985, assumes x1 equal to x2. It has only one length scale and one index scale. Sleeth stated that lambda1 dominates the amplitude and lambda2 dominates the phase. Nielsen suggested that for a fully developed turbulent flow, P1 equals to 1/3 and corresponds to the maximum energy dissipation for a fixed lambda 1. But why this correlates well with the results based on the linear ideal viscosity model is a question. These are almost all the understandings we have. We still do not understand the physics behind the defect function approach. We need to go further. Here we show the datasets we have in the space of AonKS and the Reynolds number. The red corner is the field conditions for natural sand bed suggested by Nielsen in 1992. Unfortunately, we still don't have enough data to investigate this area. We would like to expect in the region with AonKS larger than 100, the horizontally uniform condition is valid. Based on this datasets, we would like to make sure the demarcations for x1 equal to x2. Here we generally compare the quantity of x1 and x2 and plot the correlation as a function of AonKS. The effect of Reynolds number is neglected. The correlation is clear. The line separating the horizontally uniform and non-uniform flow conditions is not quite clear. The figure indicates this value might be 20, but the evidence is weak. We look further into the comparison between x1 and x2. For x1 larger than x2, we will get a more uniform velocity profile and a smaller phase shift. For x1 smaller than x2, we will get a very large velocity overshoot. However, for a non-uniform flow like this, it has better to be considered as a flow over obstacles rather than a typical wave boundary layer. Having all of this in mind, we can move on. The velocity deficit is divided as two parts: the amplitude defect dominated by x1 and the phase defect dominated by x2. DFS have two length scales, lambda 1 and lambda 2. Nielsen provided us an index parameter. Here is easily to find out these values from the figure x1, x2 against Z in the log-log scale. Lambda 1 represents the elevation where x1 being 1, and lambda 2 represents the elevation where x2 equals to 1. P1 is the slope of x1. Is the slope of x1 against Z in this figure. Apparently, there remains a P2, which is the slope of x2 against Z. However, P2 was not introduced by Nielsen. Firstly, we would like to find out the physics behind x1 and its parameters, considering the amplitude defect only, and use the form of dfn. The velocity is written with x1. Consider the mixing length hypothesis. For a fully developed turbulent wave boundary layer with AonKS equals to 10 to the power 4, the ratio of U tau on U infinity is about 0.04. We will get the mixing length specified with x1. So we can find out how x1 works. On one end, we fix lambda 1 as beta and change the value of P1. We found with P1 being 0.3, the mixing length dominated by x1 is asymptotic to kappa Z, which is commonly accepted for fully turbulent flows. Analogously, we can get that with P1 being 0.3, the ideal viscosity dominated by x1 is also asymptotic to kappa Z U tau. This is the answer to Nielsen's question. As can be seen in the left figure, P1 is a constant like kappa, which dominates the correlation of L as a function of Z. On the other hand, we fix P1 at 0.3 and change lambda 1. We find the correlation L as a function of Z is independent of lambda 1, which again demonstrates that the correlation is dominated by P1. However, we get that lambda 1 dominates the length of the region where the correlation should be valid. For example, if lambda 1 increases from beta to 10 times of beta, the region will also increase by 10 times. For convenience, the region dominated by the correlation of L as a function of Z is termed turbulence core region. For other AONKS conditions, P1 changes with the ratio between U tau and U infinity and yields similar correlation of L as a function of Z. A brief summary for X1. X1 dominates the correlation between mean flow dynamics and turbulence dynamics via P1, and meanwhile X1 confines the region where the correlation should be valid via lambda 1. Secondly, we make some further investigations on the spatial temporal structure of turbulent wave boundary layer, and meanwhile find out the physics behind X2. Recall the definitions of eta 1, eta 2. We find that eta 1 and eta 2 are directly dominated by X2, and here we introduce the parameter P2, which is the slope of X2 against Z, and the quantifications of turbulent structure is obtained. With this scale consisted of lambda2 and P2, the structure recovers to the linear form like that in laminar flow. A brief summary for X2. X2 dominates the spatial temporal structure of wave boundary layer, including several boundary layer thickness via lambda2, and the nonlinear development against the time via P2. Combine X1 and X2, we will find a way in which the defect function dominates the wave boundary layer. With these understandings, a new form defect function DFT is proposed. Comparing to DFS and DFN, it simply introduced an additional index parameter P2, which was already indicated earlier. We established the relations between DFT parameters and RE and AONKS. With these correlations, DFT can be applied as a predictable model. Then we introduced some applications based on DFT and also demonstrate that DFT works well in predicting the motion and the bottom friction factor. At present stage, DFT is workable in the region of AONKS larger than 100, which is larger than the field conditions suggested by Nielsen. Here are also some future works we need to do. Okay, that's all. Thank you.